Let's do another example that's somewhat similar, but has a little bit of a different twist. And I want to go back to the informal induction idea. We've got a sequence, 7 to the n minus 6n minus 1. And I want to just think about, how would you discover something interesting about this sequence? Well, just try a few examples and see if there's a pattern. So when n equals 0, it's totally legal to put that in. You get 1 minus 0 minus 1, you get 0. When n equals 1, you get 7 minus 6 minus 1, that's also 0. It's not going to stay that way. You could predict that pretty easily. This grows exponentially, this grows linearly, so they're not going to match each other perfectly. But it's an interesting fact that they're both 0 already. 7 squared, 49 minus 13 is 36. Then it's a little more work to actually get it, but we talked about 7 cubed in a few videos ago. So that's 7 cubed, 343 minus 19 is 324. So at any point you might want to pause the video and start thinking about, what's in common. We don't have a lot of evidence here, but you can start thinking about that. For 4, if you calculate it out, you get 2376. And we'll just go up to 5. You can do it yourself if you want to pause the video, but it's 16,776. Okay, so the question is, what pattern do we see? Is there any commonality here? And a hint, if you want it, is that it's similar to what we were saying before. There's really a divisibility pattern here. So let's see. They're all even numbers. Okay, so they're even. Okay, it's pretty easy to determine that they're actually divisible by 4. You could either just divide them all by 4, or you can observe that you can test a number's divisibility by 4 by just looking at the last 2 digits. Because after all, what you're taking away is a multiple of 100, and that's certainly a multiple of 4. We'll talk about these kind of cool divisibility rules for looking at the digits of a number when we focus more on divisibility later. So in fact, it's divisible by 4. So speaking of divisibility rules, probably the coolest one is how to figure out if something's divisible by 9. And that, to do that, you can just add the digits up. You might know that rule. And that's going to be a really cool one to explain when we look at divisibility and what's called modular arithmetic. So 3 plus 6 is 9. 3 plus 2 plus 4 is 9. 2 plus 3 plus 7 plus 6 is 18. That's divisible by 9. 7 plus 7, 14, 21, 27. All these guys, when you add the digits up, they're divisible by 9, and that means that they're divisible by 9. Oh, okay. So in fact, everything is divisible by 36. And that's as big as you're gonna get, unless you count that as an exceptional case, which we'd rather not do. So it looks like they're all divisible by that one number, by 36. Okay. So let's see if we can prove it. Okay, so I want to give a little bit of a different style of setting up a proof by induction. We're going to do a little experimentation first, and I'd like to try to avoid that adding and subtracting trick because that's not super obvious, and I think it's one of the things that people don't tend to come up with on their own. So what I'm going to do is I'm just going to play with this formula. Okay, that's a sub n. And I'm going to assume I'm not going to write it out formally quite yet, but my assumption is going to be that that's divisible by 36. And then I want to assert that a sub n plus 1 is divisible by 36. But instead of writing a sub n plus 1 down for this time, I'm just going to think about what could I do to this that's going to keep it divisible by 36 and yet get some n plus 1s in there. Okay, so and it's very similar to what we were saying before. One of the simplest ways to take a number that's known to be divisible by something and produce a new bigger number is just multiply it by something. Oh, what if I multiply it by 7? So again, here we're just playing with the nth term, and we're trying to see if we can get the n plus 1 term or something close to it. Okay, so that's 7 to the n plus 1 minus 42 and minus 1. Well, that's exactly I'm gonna get if I look at a sub n plus 1, except that this is different. Okay. Okay, but let's see what that's going to be. Okay. And let's see, let's take out a 36. A 36 n, and then what's left over is going to be a 6n minus 7. Ooh, yeah, very important. I didn't correctly do the 7 there. Ooh, okay. Huh, okay, so now the cool thing is this is for free. I don't care about this at all because it doesn't change whether it's divisible by 36. So I'm taking something that's divisible by 36, multiplied by 7, that's definitely divisible by 36. I could add this back in to get rid of it, and it'll still be divisible by 36. Ah, okay. So, and then what's the rest of it? Ooh, I'm going to write this 7 as a minus 6 minus 1. Ooh, what's this? That is minus 6 times the quantity n plus 1. Aha. Okay, I think we're on a roll here. So let me just write that out a little bit more cleanly. So what did we do? We took 7 times a sub n, that's all this stuff, and then that plus 36n is everything I've written down here except without that guy. 7 to the n plus 1 minus 6, factor out the 6, n plus 1 minus 1. Guess what? That's exactly a sub n plus 1. Okay, so now we're ready for the proof by induction. Okay, so base case, well, we did a plenty of base cases, okay? N equals 0, or if you like, start at n equals 1, or n equals 2, 3, 4, 5, we checked them all. Okay, so that's good. Okay, don't forget that though, because you can get into real trouble not proving your base case. Any inductive step. So we're going to assume a sub n is divisible by 36. And then I've already done the key calculation, I'm not going to redo it. A sub n plus 1 is 7 times that number that's divisible by 36, plus 36n, which is divisible by 36, is also divisible by 36. Okay. And if we wanted to be really careful, we'd say, therefore, by induction, this is true for all n. Ooh, you know what? I didn't change n to k, and that's because I'm not used to that, to be honest. Okay? And it's okay to not worry about the letter change. If I was following the exact style before, I would have changed the n to a k in all these calculations. But of course, letters don't fundamentally matter. Okay. So that's a little bit more focusing on exploration. What would you guess based on the numerical evidence, and how would you go from this to build an inductive proof as opposed to sort of assuming it's going to work and using sort of special tricks to do it? So I think that's a little different.